Good morning, everybody. I'm Sunil. I'm a solutions architect in the deep learning team at AWS, and I have Miro here, who's a solutions architect at NVIDIA. And we're going to be talking about deep learning with MXNet and Gluon today. So here's the agenda. We'll start with talking about AI at Amazon and how we've been working on AI technology for about 20 years. We'll talk about how do you do AI at scale. We'll do some introduction to kind of level set here. And then we'll talk about how we can visualize deep learning models. We'll then go to an overview of MXNet, and then what's this Gluon all about. And we'll try and live code and show some code and see how easy it is to use Gluon. We'll look into some customer stories, and I'll leave you with some resources that you can get started with deep learning with MXNet and Gluon. So AI at Amazon hasn't been recent. We've been deploying AI technologies and building them for the last 20 years. And one place where we can see this is actually at our logistics center, where we have robots that are actually trained to bring tasks. So the people actually don't go and fetch when you make an order at Amazon.com. The robot actually gets it to the people, and then they assemble your pack. Another innovation which is quite recent is Amazon Go Store. You might have seen videos of this. This is a store where you can walk in and there's no checkout lines. It's almost shoplifting. So you literally take something and it's all computer vision algorithms that are looking at detecting your face, detecting the object that you have taken, and all you need to do is scan in when you come in with your mobile phone. The rest of the thing is automated. So how do we think about the AI stack here at Amazon? So the three main layers about the infrastructure layer, which is the framework layer, the platforms, and the services. The services are where we expose deep learning APIs, where you can vision APIs, we have language APIs. In the same way, platform is where you can process the data and use some of the services like EMR, Spark, and build machine learning algorithms and tie in there. The framework layer is where we're going to concentrate today. This is where the bleeding edge technology, where people want to build their own models and deploy them, tend to use that. So what we wanted to do is make it easy for you to use deep learning, regardless of the framework that you wanted to work with. So what we did is we actually built an AMI, and it's available at no additional cost. So it comes with all the deep learning goodies that you would need and data science packages. So like SciPy, NumPy, you even have all the frameworks here, which is right from MXNet to TensorFlow, Keras, Caffe, Torch. All of that is available in the deep learning AMI. More importantly, it does come with the NVIDIA CUDA packages so that you don't need to install them. So in less than 2 minutes, you'll be able to set up your machines at one click. And we also have made available a CloudFormation template. So let's say you want to do distributed training, like you have terabytes of data, it probably doesn't fit on a machine, you want to train it fast. So to facilitate that and make it easier, we have a CloudFormation template that actually sets up the infrastructure for you, which is available with Apache MXNet and TensorFlow as well. Now, let's do a brief, what is this learning in deep learning? Let's take a look at that. So we have three distinct layers that we described in a neural network. The first one's the input layer, which is blue here. The gray are called the hidden layers, and the red layer is the output layer. Now the idea is you send the input that you have into the network, and you do this repeatedly, and the network learns. Let's see how this happens. So the input actually goes through the node. We do some computation. So we can see here the nodes are connected to one another. So these edges are actually initialized. You can do random initialization, but there are initializing techniques. But more importantly, you can think of this as these are weighted edges. So you do a matrix multiplication, and then what we do is, you might be familiar, we actually have an activation function. So the idea here is to add nonlinearity to solve complex problems. And then we do that until we get to the output. So we get a mathematical output. Say, in this case, we went from we label y, and we get y prime. Now, y prime may not be equal to y because, remember, we did a random initialization. So the idea is, how can we get y as close to, or y prime as close to y here? So this is, what we did was, it's called a forward pass, right? We went through the network. Now what we do is a process called as backpropagation. And the idea here is we're trying to find the delta that is defined by the loss function. I won't go into the complexities of that, but here's the intuitive idea is we're computing the delta, and what that does is we now apply the delta back so that we correct the weights so that we can find the right weights to match the label. And this is what we do for all the inputs that we have in our data set, right? That's how the network eventually learns. It's the same process, so you correct the weights, the activation function, go back and correct. And usually this process, right, like let's say we have 1,000 samples in our data set, we run the 1,000 samples, and we'll run them many times. And each time the network sees the same data set, we call it an epoch. So we'll do several epochs until the network converges. Now, there are various network architectures, and I'll go through briefly with two of them. So one here is called a convolution network. And it uses the concept of convolution. So convolution is defined as intersection between two functions. Now, what happens is based on different problems. So in computer vision, spatial information and local information have a lot of significance in what you're trying to, let's say, your detection or recognition sort of a task. Now, what convolutions are good at is, remember, they're intersecting between two functions. So what we can do is define filters or learn these filters to find the right features that actually influence the problem. And so we'll use what you see on top there is a filter matrix, which is on your input matrix. So you've got a 2D image, and you have your filter that goes through and extracts these features. Now, that's again, let's say we're classifying a cat, we're identifying an image as a cat or a dog. We'll run the filter, extract these features, go through the layers, and we'll have a fully connected layer, a similar network that you saw earlier, to get all the learnings together, and then finally find the probability as to, okay, I think this image is 80% dog, or so on. Now, not necessarily every information, every problem is sort of image related or require local spatial information. So, especially with context related tasks, and one of the examples is say in natural language processing. Let's say you're doing sentiment analysis. So there is a dependency on something that might have happened a long time back. You want to capture that, or time series behavior. So this is really well captured with recurrent neural networks. The idea here that the network has a self loop. So you're sort of feeding the same input back after certain processing into the same network. There are extensions of this where you can have memory, and which we'll go through a little later. The idea is it can store state so that we can use later. Because remember, in time series data or natural language processing, we can have long-term dependencies. So I'll switch over to Miro who's going to talk about idea of deep learning, the story, and how this AI and deep learning fits in.
Thanks, Sunil. Appreciate it. Thanks, guys, for coming out. So, as Sunil was sort of painting this picture, deep learning is just, one of many machine learning methods that we have at our arsenal. And if you just look at it on the surface, it's hard to know why we should be excited about deep learning specifically. So if you again look at the field, AI is the broadest context. Machine learning is a subset of AI, and then deep learning is a subset of machine learning. And if you look farther inside of machine learning, you'll see that there are many different tribes, if you will. These are different ways that people have thought about learning from data. And there's the symbolist tribe, which is probably some of the earliest folks in computer science. These are folks that like to use philosophy and reason, and this is where you might find rule-based systems. We've got the analogist camp. These are folks like support vector machines and clustering, where you're essentially using a distance metric. Whenever you're presented with a novel item, you reason about everything else that you know about, and you use some kind of a distance to say, oh, well, the thing you've shown me looks closest to this other thing, so therefore that's my answer. You've got the Bayesian camp, which is folks who typically like to make their assumptions clear up front. They like to generally, create the key actors in a decision-making problem, express them as nodes, connect them up in a graphical way, and then use formal methods of updating the connections between them based off of the statistics and uncertainty in the data. You've got the evolutionist camp. These are folks that sort of take inspiration from the way that we understand natural selection to work, where you've got some kind of a fitness criteria. You may have many models competing at the same time. Those that do well will get to create more copies in the next generation. They get mixed together with other competitors that are successful, and you throw in a little bit of randomness. The connectionist camp is where sort of deep learning lives, and we'll be doing a deep dive on that today. These are neural networks folks. And then the last camp are boosters. So this is generally things like random forests, things that are very successful in machine learning competitions on small data sets. So the idea here would be that if I present you with something from your data set, a particular example, you can build a decision tree. In this decision tree, it's almost like playing a game of 20 questions. Like, what are the right questions to ask to figure out what category this thing belongs in? If you build one of these decision trees for every example in your data set, you now have a forest of trees. And so whenever a novel question comes along, you can just allow it to propagate through all of the trees in your forest, take the average, and that's your solution. So this is just a very sort of high-level perspective on some of the things that people have done when they're trying to learn from data. There's many others that are not on this slide, of course. And there's many strengths and values to each of them. So why should we care about deep learning specifically, especially if you've got one of these other ones that works quite well? Probably the biggest reason is that we as a society have marched to the right-hand side of this plot, where the x-axis represents the quantity of data that we have. And as we sort of look at what was happening in the past, maybe 5-10 years ago, I would make the statement, and it's somewhat inflammatory, perhaps, that the order of these machine learning schools of thought, as far as their performance rank, was largely driven by the amount of motivation that a data scientist had to spend their human effort coming up with features that capture some kind of an essence of the problem that you're studying. And so if you spent heroic amounts of hours coming up with the right representation for your data, maybe you outperform everybody else just through sheer willpower. The thing that we're seeing more and more so these days is that is now being replaced by models that have so many parameters and have a chance to stream through so much data that human effort is being switched to a different task. And so specifically, when we look at deep learning, what we're seeing is that small networks might not perform too well. Large networks, or let's say medium networks, will do quite well and be competitive with all of the other types of machine learning methods. And then really large networks or deep neural networks will, in some cases, exceed human performance or set new records. And so this is probably the #1 motivating reason why people are excited about deep learning. We still don't have a truly deep, fundamental theoretical understanding of why it is that it's the case that deep learning is performing so well. In some ways, it's almost like engineering back in the days before we had the laws of physics. if you look at the papers that come out in the field, every week a new paper comes out and says, oh, I built a deep learning network to do recommendation for my website. Or, oh, I built a deep learning network to help me drive my autonomous vehicle. And the guys who are writing these papers are really smart folks. And each time someone writes a paper, they sort of share their thoughts. And it's almost like going back 500-600 years and looking at what bridge builders or engineers were doing, where one guy would come along and say, I built a bridge using pillars and it stood up. Or another engineer, maybe a gal, will come along and say, I built a bridge using arches and that stood up. But we're not yet at the point where you can submit a blueprint of a bridge and using the laws of physics, make a claim about whether or not it will stand. That's kind of where we're at with deep learning as well. We don't know beforehand if a particular problem and a particular suggested architecture will work well. And so in order to sort of make progress, we need to do a lot of experimentation. But nonetheless, empirically, this is what we're finding, is that these models are outperforming everything else in the field. And so part of what's making this approachable and exciting are tools like MXNet. This is the deep learning framework of choice at Amazon, came out of Carnegie Mellon and University of Washington. And this is a really powerful tool. It allows mere mortals to jump in and with a few lines of code start instantiating these models. They're very, very powerful, can consume large data and learn from it. And so, you just pick your favorite high-level language, Python, R, MATLAB, JavaScript, C++, the list will keep growing. And in that high-level language, you define your neural network architecture. And once you do, MXNet will take it, it'll create a compute graph from it, which essentially represents the nature of the computation and potentially compile it again to your destination hardware platform, whether that's a mobile phone or a server in the cloud. And I highly encourage you to dive in and play with this. We'll do a quick demo of it coming up here in a bit, but it's a great tool. And the next sort of piece of the puzzle is, now we're properly motivated to experiment with deep learning. We have the software tools. This is the hardware tool. This is the thing that allows you to try 1,000 different bridges to see which one will stand up. And specifically, this is the Volta. This is NVIDIA's latest and greatest GPU, born and bred for AI and deep learning. It's got more than 5,000 cores, some of which are hardware dedicated for matrix and tensor operations. It's got special interconnects so that these guys can talk to each other at rates that are magnitudes faster than regular PCI Express. And you lucky folks have them in your cloud in the form of the EC2 P3 instance. These guys are so powerful. I've had a chance to play with them. It's like 1,000,000 times faster than the laptop you took to college if you spin up a cluster of these. So this is a truly remarkable piece of hardware. This is what enables you to do deep learning at scale. And what you do essentially when you're doing this at scale is you use multiple workers or multiple GPUs to solve the problem together. So if you have a data set, which is what's shown here at the bottom of the slide, you split it up, you send unique pieces of it to different machines, and each of those machines gets to see that unique subset of the data, allow that data to pass through it, come up with the suggested learnings from each data sample, and then average those together to build the next model iteration. So in some sense, this is like, if you had to study for a test and you had to read an entire book, you can clone yourself multiple times and give each of your clones a different chapter to read. And then, presumably your brain will change in some unique way as a result of reading each chapter, and you can sort of average those changes together, and that's like you sequentially reading through that book. And so that's the idea here with this distributed learning process. Just to sort of take this to its conclusion, each of these workers shares their learning with a parameter server, and then that parameter server aggregates these learnings and produces the next generation of the model that gets sent back down, and then it's ready to ingest new data, and so on and so forth. And this is what's powering some of the breakthroughs in language translation, autonomous driving, Amazon Go, all the stuff that you guys are doing, these principles are behind it. So let me show you a quick demo here. Uh-oh, let's see. So here I've just got a P3 instance running. And this is something that you can also spin up very easily just by going to, your EC2 management console, choosing to launch an instance. I don't know if you guys can see this text. Let me make it a little bigger. And so if you go to the AWS Marketplace and you search for deep learning, you have many different choices that you can choose. Deep Learning AMI is a great one. So you would maybe take this one. I'll be using the Deep Learning AMI with CUDA 9, which allows you to use the Volta instances. And then this is, telling you it's not going to be free, of course. And then you would come along and you would pick your instance of choice. In this particular case, I highly urge you to try the P3 instance. You can go up to, these are your choices here. Let's assume you pick multiple GPUs. You would review and launch, and so on and so forth. And then this would essentially land you, assuming you SSH into it, into a terminal that has very fast hardware, very fast drivers on top of it, and a software stack, as Sunil was mentioning, that's optimized to support any of the deep learning frameworks that you could possibly think of running today. And so this is what that looks like. Let's see. This one. So, if you spin this up, this is what you're greeted with. And, welcome to Ubuntu 16.04 long-term support. And this is the deep learning AMI. You can launch Python. You can import MXNet. And now you can do deep learning. You can, this is, I think, MXNet version 12.0. Yep. So latest and greatest MXNet ready to roll out the box for you. So for the demo today, let's actually do something with MXNet. Nope, not the localhost one. Okay. So here, we'll spin up a notebook, an interactive Python notebook. And in this notebook, we'll just be doing a very small toy problem where we're going to try and predict how long it takes us to get to work if we were to leave from our house at a particular time of day and given a particular weather condition. So what we'll do is just import some libraries here. And then, this is our problem. Because we're doing this synthetic data set example here, we'll sort of take on the role of the traffic gods, if you will, where we get to generate this data, which is not typically what you would get to do as a data scientist. But first we'll determine that the relationship, essentially the duration of the commute, is determined by when you leave and the weather conditions, and specifically, these are the two underlying relationships that are critical. So the time of day that you leave, if you leave in the morning, very early in the morning, it's okay. But if you hit morning rush hour, it's going to take you a long time. Lunch is a good time to be on the road. Afternoon commute is bad. And then very end of the day is okay again. And then the weather severity, as the weather gets worse, you're going to be stuck in traffic longer. If you combine these two factors together, you end up getting the surface. And this is essentially the surface that we'll be sampling from. But first, we're going to create data. And the way that we're going to sample from the surface, now we're putting back our data scientist hat on. And here, we don't actually know what this blue surface is. This is what the traffic gods determined for us. So what can we do? We can sample data, and we can try to build a model from it. And the way that we sample this data is by driving from home to work and then recording what happened. So specifically in our logbook, we would keep track of when we left the house and what the weather conditions were and how long it took us to get there. And each of our observations is essentially one of these red dots that you see here. And there's many of them because our logbook maybe lasts multiple years. But the idea is that we don't actually have direct access to the blue surface, but we can sample from it using these red dots, our trips or observations. And can we build a model such that given a particular mixture of departure time and weather conditions, can it predict for us the duration? And so we'll do the classic machine learning thing, which is we'll take our data set, we'll split it up into some 75-25% order, let's say, where 75% of the data we'll use to train the model and 25% of the data we'll use to test the model. And so this is what we'll do next. And the idea is that our model will learn this function. Initially, it will be very bad because the parameters are randomly initialized. As it gets to learn, it'll get better and better. And at the end, fingers crossed, it'll have learned this function. And we'll do an interactive visualization of this process. So let's go ahead and actually, generate all the stuff we just talked about. So first we'll generate, the data set, and we'll generate our samples, our logbook. And our logbook, essentially, just to reiterate, is represented by these red dots that live on top of this blue surface. And you'll notice the red dots don't exactly fall on the red surface, which is kind of realistic because in most conditions, you don't actually get to sample without noise. So next, we'll do some MXNet. So essentially here, we create these data iterators. So this is just our data set. We're now getting it ready to be ingested by our model. And these data iterators are something that if you were to use multiple workers, this is very helpful for that because the different workers can read without running into each other. So once we create these data iterators that give us access to our data, we can start to actually define our model. Here, one of the important parameters that I'll highlight is this batch size. This is something that is really critical to fully saturate your GPUs. Let's set this number to be kind of low initially, maybe 32. This basically means how many forward passes of data do I get to take before I make a single update to my model. If this number is very high, then you potentially could wipe some of the learning that's happening because you would be seeing lots of samples, but only changing after you average across all of them. And so initially, you kind of want your batch size to be small, but eventually, once the network starts to move in a good direction, you can change this batch size to be very large so as to fully saturate your GPU. So let's start with the simple case when this number is low. Here are the lines of code that define our network. Ooh, maybe zoomed in a bit too far. So this is MXNet now. And so here we're basically saying that we're going to have input data is coming into our network, and then we're also going to have the particular target variable. This is the commute duration that we're going to be training for. And here we're defining our layers of the network. And so we've got layer 1 is connected to the input, and it has 5 neurons. Layer 2 is connected to the one below it, and it has 27 neurons. The layer after that has 20 neurons, and the layer after that has 40 neurons. And so these layers are all connected together in a successive fashion. They're all ultimately leading up to this layer that is comparing the prediction of the network to the target label variable, which in this particular case is the commute duration that we got from our logbook. So once we create this network, you might ask, what is this weird shape? What are these numbers? We can visualize what it looks like. The default visualization tools from MXNet show you something like this, where you can essentially see that the data is coming in, it's going to 5 neurons, it's getting activated by the sigmoid function. This is probably the most classic activation function in deep learning, inspired by the fact that when the computer scientists were first looking at this, sigmoid function kind of replicates the behavior of real neurons. So it sort of looks like this. And the idea is that it's either 0 or 1, or it has a ramp in between, and it's meant to replicate the behavior of a neuron that's either firing, not firing, or in a transition stage. And also, as Sunil was saying, this also gives you the capacity to do more complex stuff because it's now a nonlinear function. So anyways, we've got 5 neurons having the sigmoid activation functions connected to 27, connected to 20, connected to 40, connected to 1, and that 1 essentially is a prediction of how long it takes us to get to work. This particular structure can be visualized in a different way. I wrote a little visualization script here that helps us see it differently. So this is the same network now laid out graphically, and it's got this weird shape. It looks a little bit like NVIDIA's latest headquarters. Not really, but kinda. It's very easy to change this architecture. With a single line of code here, we can perhaps make it something like what you might do if you were doing this for real, where you would probably set all of these values to be the same number, as opposed to trying crazy things. And so, the neural network might look like this initially. This is probably a more realistic first experiment to run. But whatever you happen to do, this is the heart of deep learning and data science. You're going to be doing lots of experiments. And so once we've got this architecture, we can train it. And training it with MXNet is very simple. You can use the high-level API, which all you would need to do is do this. Basically, you say, model.fit, tell it how many passes through the data set you want to take, tell it what kind of optimization method you want to use. Atom is one that allows you to actually keep statistics for every parameter or every weight in your network. And so each of them can learn at their own rate. So this is a pretty fancy and pretty good one. And so this is all it would take to actually train this network. This is a slightly more verbose version of that same training procedure. This kind of goes along with what Sunil was saying, where you would do a forward pass through the network. You would then compare what the prediction of the network is to the true thing you're trying to learn. You would use that difference to do a backwards pass to update the weights, kind of like a credit assignment problem, and you would ultimately apply those changes to the network. So what I'll do here is just, take this training loop, and I'm going to sort of add a little bit of code around it just to make it so that we can dynamically visualize what's happening. And so let's do that now. Let's go back here to our visualization. And here you can see the network predictions over time. Essentially, you can see this sheet of the surface that the network is using to learn, and you can see that at the very beginning, it sort of was randomly initialized. All of the weights didn't really know anything about this problem, but very quickly, it's starting to actually converge on a good solution. While this is running, let me see if I can pull up this guy, which is essentially showing the utilization of the GPU while this is all training. You can see the GPU is being utilized around 23%. The Tesla Volta 100, which is what's in this machine, is a very performant piece of hardware. We're barely making it sweat here with this toy problem. In practice, when you bring a data set that you care about, that your team cares about, typically this is going to be something that you would want to distribute not only on the GPUs within one machine, but potentially have multiple nodes working together to solve this problem collaboratively. And MXNet, I would argue, is the best at doing this distributed training out of all the networks currently. Okay, so here our GPU is back to 0, which means we finished the problem. We probably, did a little bit of overkill here. This network clearly learned. Let's do one little modification where we'll now change the batch size from 32. Let's set it to 512. So before, we would see 32 examples from our logbook and make an update to the network. Essentially take the average deltas or the average changes from those 32 examples and apply them to our parameters. Now we're going to take 512 examples before we update our model. So we're going to be looking at a lot more data, and in some sense this will allow the GPU to use more of its cores to do the forward pass before having to do a single backwards pass. So with this single change, we can now run it again in Actually, I don't know if I'll be able to be fast enough to show you guys this, because now it's just going to go really fast. Actually, before I do that, let me see if I can show you the learning curve of what just happened. So when we were going slow initially, this is what our learning curve looked like. We were going slow, but we were learning very quickly. Now we're going to go much faster and maybe not learn as quickly, but it'll be a trade-off. So now I think we can redo this training. Yeah, it's screaming fast. I don't even know if I can. It's almost, it finished before I got there. So now you can see the network actually hasn't even maybe reached convergence because it went so quickly. This is what you do by saturating the GPU. Let me change the batch size just slightly so you guys can see it. But actually, you know what? We're running low on time, so I'll just take my word for it. In this case, when you change the batch size by a factor, by an order of magnitude, this utilization goes up, right? Because essentially the GPU can do more stuff. And these are the kinds of trade-offs that you might see when you're doing your experiments. So let me show you one final thing here. Actually, let's run this network a little bit longer so it can maybe converge. Let's do 500. And again, it'll go extremely fast now. Okay, it's done. Let's plot the learning. Okay. And let's look at just a couple little things. So, actually, you know what? I would need to restart this process. I'm sorry, give me 1 second. Let me re-randomly initialize the parameters before I do the learning. Okay, there we go. And it's done. Okay, now this is the learning curve that we have when we have our much larger batch size. You can see it's not as clean as the one when we're only taking small steps before we do updates, but nonetheless, it goes much quicker. And so what you'll see, oh boy, here is that at the very beginning, when we started this problem, in pink are the predictions of the network. And so before it saw any of the training data, it was kind of clueless as to this particular surface that it needed to learn from. Midway through the training, it seems like it actually got most of the problem correct. It seems like it could improve a bit in this sort of late afternoon traffic and maybe some of the morning commute traffic. Let's see at the very end of the learning process what happened. So after all those passes through the data, it seems like it got pretty much everything correct. Maybe a little bit of room for improvement here on the late afternoon traffic. But this is essentially what you want to see. You know, when you're a data scientist, you come up with some kind of neural network architecture, you stream your data through it, you know, you cross your fingers and you pray, and hopefully at the end you get something like this, where you've done a good job fitting this particular model. And so with that, my demo is over. Thank you. We need to switch laptops. Switch laptops or slides?
No, slides.
Okay.
Thank you, Miro. That was excellent. You know, you guys have a great idea now as to how the neural network learns, what's happening through each of the epochs, and some of the effects of batch size and learning rate. So thank you, Miro. So let's look at what's MXNet here, right? So why does MXNet like perform, or people love to work with MXNet? So one of the aspects is the front end and the back end is decoupled. So what happens is no matter what language you write in, it gets all the bindings are called, which are written in C and C++, so that you're not sacrificing, because certain languages, you know, based on how they're built and their runtime can be slower. You can actually write anywhere from Python to Scala, R, Julia, Go, in any language, and you don't necessarily pay the performance impact. and there's even a Perl binding. So somebody actually went ahead and wrote a Perl binding, so you can write neural networks in Perl and compile that and work with the MXNet backend. What I want to do is actually show you guys kind of a comparison as to between like some of the most popular ones, Apache MXNet, TensorFlow, and CNTK, as to how much effort is it as you get started to get going with the number of source lines of code and kind of a benchmark. And also, we do have a memory footprint. As you can see, the code then for the canonical AlexNet network is about 44 lines of code. And the standard LSTM, which we benchmarked, we got about 2.6 gigs. So, which is super interesting, because when we actually deploy on devices where they're memory constrained, you want your networks to be not beefy. You want them to be slim and deployable. Now, having said that, like, why Gluon, right? Like, what is Gluon? So this is actually a project in collaboration with Microsoft that we developed this interface. So we listened to our customers, and one of the things was developers like to think like developers. So what that means is, in traditional, if you look at other frameworks, you can have two levels of language. There's one, the neural network language that you write, and that gets compiled, and then you're running the actual machine code. Now, the language isn't very close. Let's say you're using Python. It doesn't seem Pythonic. So we wanted somewhere where to bridge the gap and make it where it feels like you're writing Python. You can use it just like any other language. So the idea was to come up with this syntactic sugar, which is Gluon. So first thing is it's simple, because your writing is just like any other language that you do. Plug and play, building blocks, extensible. You can write classes, extend them. So all that goodness comes with this. So the next thing is flexible and imperative, right? You can now actually write loops. You can give conditionals. You can even put, my favorite part is, you can even put PDB in case of Python, put the debugger, and debug through it. Super helpful. Dynamic graphs. Now, especially when you work with, if you think about, I assume a lot of people here are familiar with stack memory and heap memory, right? So static memory, you allocate, you pre-allocate, you're fixed, you can't change your array size. Well, there are other data structures where you can use where you can assign memory, or you can request memory from the heap and make it dynamic, right? Like expand on the memory. Similarly, you get that concept here. You're not necessarily bound to a static graph. You can change the shape of the shapes. Pretty useful when you're dealing with neural net NLP data sets or problems where you might need variable length inputs or output layers. Now, performance. You don't necessarily pay for the performance hit because, again, there's the decoupling that I talked about. And Gluon is an interface, right? Like you can actually have different backends as well. So technically speaking, you could use TensorFlow underneath as well. So the idea is, as I said, like you're writing it, you're still compiling to the backend. There are other tools that I'll show. There's some tricks where you can actually convert the Gluon code into a symbolic network to achieve faster speed as well. So it's pretty flexible in whichever way you want to run. So let's actually look at how an application, a Gluon application. So let me just get my laptop set up.
You my cable, right?
Yeah. We don't have enough time to live code, so I'm going to show a couple of samples here. This is to build, we went through what a convolutional network was, right? So if you go to gluon.mxnet.io, extensive documentation, it's kind of meant to be a deep learning book. So even if you're new to machine learning or deep learning, great resource, go in. There are chapters that walk you through how you can get ramped up and build these networks. So in this case, we'll go through the data set. So we'll use the ever-famous MNIST data set here to classify handwritten digits. So essentially, we have data where we have digits that are handwritten 0 to 9. And the idea is, can we build a network to classify that, hey, that's a 0, that's a 1, and so on. The first part here is actually loading the data set. So we've made it easy. You can use the MNIST data set here that's provided part of the framework. You do that, and you can load the data with the data iterator. So next kind of magic is we use the sequential object here, and we actually put it in the net.namescope so that each of the layers are named in the same way. So it's like layer 1, layer 2, so on. So it's easier when you kind of view the network to debug through that. So in this case, what we have is a 2-layer convnet. So we have a conv layer with 5, the kernel size of the filter. Remember the filter that we went through, so size 5, 20 of those. And then we'll use the activation function relu. So Miro talked about sigmoid. Sigmoid has some shortcomings. So we use a continuous function where everything, relu is just a rectified linear. So essentially everything less than 0 is 0, everything greater than, just it's a monotonically increasing function. What we then do is we actually collect, so we call the collect params, and we initialize the weights, and then we can define a loss function. In our case, because we're doing a classification, we can use a softmax cross entropy loss function. And the trainer, so we can define, so in this case, we'll use stochastic gradient descent, which is the basic, the advanced atom that he was talking about, but you're free to choose. And the training loop, as you sort of see here, it's pretty Pythonic, right? So we're writing a loop. You can debug. You can put a breakpoint. It's pretty flexible. So if you want to make this into a class and kind of reuse, you can do that. And which is what I'll show you guys. I've done for another example here. So this is, I'll show how to use the recurrent neural network in Gluon. So we have, so the problem at hand is a human activity recognition. So this is a data set which is available free from UCI, which is recorded the gyroscope information through one of the smartphones. So what people have done is activities like standing, walking. There's a fun video in the data set that how they show how the data set has been collected. Now, using these XYZ axis for each of those sensor, the idea is, can we actually build a model to say that the person was walking or standing, or right? Like, it's a, think of this. How do if I just give you a still image, how do you know the person's walking, right? Or just standing? It's difficult, correct? Like, we need the time component. We do need a few of those samples in time to actually classify or identify what the activity is. So let me just execute the cells. So good thing is the data set already comes with the test set and the The training set, so in our training set, we have about 7,352 samples. As you can see, the sensor signals like the accelerometer and gyroscope were pre-processed, and they've already given us in that window size, so 128 readings per window, which is why when you see the shape of one sample, it's 128,9. So let's load the data, and we have about 3,000 samples in our test set. But what I've done is I've actually written a base classifier for RNN-based classifier that you can extend, and that does pretty much all the heavy lifting you need. So, for example, it'll build the model. It'll compile the model if you just give it a loss function. There's a top K accuracy metric. There's an evaluation metric that you can override, and there's a function you can just literally call the fit function, where you can specify the train data and the test data and the number of epochs it's just going to run, and you can just apply to this any problem that you want that requires or you want to use an RNN. Now, here's literally what the network looks like with that code. So all you need to do is specify a context variable, right? So in this case, we'll use a GPU. We'll get the model instance. We'll give it, hey, my output layer has, in this case, 6 labels, right? So it'll give 6 labels, RNN size. You can specify, hey, I want 128 node or 64, 32, however big you want the network to be. And the number of layers, I want 2 layers or 4 layers or 1. And that's about it. And then finally, you call the fit function, and that does all the magic for you. So let's kick off training and see what happens. The thing is, the GPUs are pretty fast, and you can see you get the batch accuracy on each batch, then you get a final accuracy, and I think we're starting off at 35% on our training set and 35% on our validation set. And we're kind of going hand in hand, which is cool. But the idea is, now, this is all, as you can see, right? Like, it was so easy to write or extend that code. We can even, let's say I had some issue where, hey, I didn't know what's happening here after predictions, right? So I can do this where, right, I can actually debug through how my prediction shapes are. Maybe I didn't specify my data set correctly. So you can actually, this makes it easy for you to debug. So I think that's the greatest advantage that Gluon brings. So as a developer, it doesn't feel like you're coding in a completely different language. It feels like a first-class citizen. And so what we can do is, sorry. So that's just the plot. As you can see, I think I did 5 epochs. So the blue is the loss function line, so the loss decreases. That's a good sign that our network trains. And if you look at the accuracy, it goes up from about 30% to 70%. I ran it only for 5 epochs, but if you run it more, you can play it. So it makes it easy for you to play and extend what we have here. So I'll share the code link soon. Let's go back to the presentation. And I have to, yes. We'll do a little recap on where the project and code is. Yeah. It's back. All right, we're back. So recap. Like this is how many lines of code it takes to write a CNN. It's really simple. And symbolic MXNet as well. Like it's not that it's not more verbose, but the idea, as you said, like as I was talking about, is the ability to debug, ability to write it in an imperative fashion versus symbolic. That's the trade-off here. If you're looking to implement object detection with the two projects here, MXNet, symbolic on the left side, and right side we have the Gluon one. So all these resources, if you go to gluon.mxnet.io, you'll be able to get a hold of this. Sequence-to-sequence model, we have a project on AWS Lab called Sakai. It's available. It's an open source project. You can use that to build your neural machine translation or any other sequence-to-sequence modeler. So any kind of conversion, for example, this example shows you how to convert German to French, German to English, and so on. So as long as you have the data corpus, you can do that. For recommender systems, using a method called deep matrix factorization, we have an example here in Apache/incubator MXNet repo. For generative adversarial networks, the link below, we have a project. Again, it's part of the incubator MXNet examples. You'll find, so these networks are really good where you can take a subset, where if you don't have enough training set or you wanted to generate images for something, all the cool research that you see and the fun stuff is all using generative adversarial networks, or GANs. To quickly look at some of the customers who've been using MXNet, SIGOPT is a great example. They're hyperparameter optimization platform that allows you to kind of find the right parameters to get the most out of your network. We also have TuSimple, based out of China. They've actually built this mask RCNN kind of approach to do segmentation in real time to help them build autonomous technology. We also have gumgum, who's been working on using this for targeted advertising. They have a great blog post on our AI blog where they're using real-time social media data and modeling that to do better targeting on ads. For symbolic MXNet, here's a cheat sheet that I've developed where you can use this to kind of get started building your networks. So if you want to know more about deep learning, here are some of the talks at our Deep Learning Summit on Thursday, November 30, where we have professors from various different universities talking on topics all the way from video modeling to robots. It's going to be fun, so register. Seats are going fast. And thank you. Thanks a lot for staying. And if this is useful, please let me know. If you have questions, we'll be available. Thank you so much.